Hello, my name is Daniel Gustafson, and this is Lab 3. So the first part of this lab had us dealing with a DC circuit, which is a direct current circuit, which means there's either like a battery or there's another power source that is flowing current through this circuit. So my prediction for the different currents, so I1 and I2, was that they would be the same since there's only one loop, so that means there's only one way the current can flow, and it'll be the same on both sides of the resistors. My observations were correct. Both ammeters read 0.02 amps. And when we reversed the connection of one of those ammeters, it showed the exact same magnitude, but with the opposite sign. Now, when we replaced one of those ammeters with a voltmeter, we get a potential difference. This is because there is now a gap in the circuit, meaning it is open, and electrons and current builds up on those two ends of the open circuit, and now there's a potential difference between those. That's why the ammeter reads 0.00 amps, while the voltage on the voltmeter reads 3 volts. When we close the circuit back up, we can see that current is going back through the circuit as our ammeter now shows 0.02 amps again. Now with the voltmeter, we can go around and check all the potential difference, all the volts between different positions like C and D. That first resistor of 47 ohms, it has a voltage of 0.96, while the ammeter has a voltage potential difference of 0 because there's no resistor, there's no battery that's increasing current or slowing it down, so it's 0. Now the round trip of all of these voltages should equal 0 because that is the loop rule, which as we see here, it does when we add them all up. Here we can see the potential versus position graph for the circuit we are working on. When we start the voltage before position A, which is below the two batteries, and then go across that, it increases to 1.5 about a quarter of the way through, and then stays stagnant until it hits the other battery, and then it jumps back up another 1.5 volts to a total of 3 volts, which stays the same all the way to C, and then it drops down just a little bit when it goes through that first resistor, and then it stays the same from D to E, which is just a space between the two resistors, and then drops all the way down to 0 volts after that last resistor. So here we have a few questions for the voltmeter, and we're going to calculate the potential differences. So first off, why does the ammeter not change when a voltmeter is applied? Well, in real life, a voltmeter has high enough resistance to where the current cannot flow through it. So current cannot exchange through the voltmeter, meaning it has to stay its course in the circuit. With that, the ammeter doesn't change in the circuit because the current is still only flowing through the circuit. When we connect the voltmeter across the 100 ohm resistor, it still is 0.2 amps because that's what it is around the entire circuit. When we place an ammeter in parallel to that 100 ohm resistor, now that current has another way that it can flow. And since ammeters, especially in the simulation, have no resistance, the current is going to take the path of least resistance. As we can see in this diagram down here, the arrows of the conventional current completely skip that 100 ohm resistor and just flow through the ammeter. Now when it does that, it increases the amps. So it went from 0.02 to 0.06 because there's now less resistance in the circuit. Now when we calculate the resistance for each parts of the circuit, we use our equation where the voltage, the change of potential is equal to the current times the resistance, and we can rearrange that to where the resistance equals the change of potential over the current. So for each of these, we can calculate out the resistance in ohms of each of the points along the graph, circuit, I mean. Now we will switch our focuses to an RC circuit. RC circuit is just a circuit that has a resistor and a capacitor. So in this circuit, when we first start out, the bulb shines bright, but as it goes through, the capacitor charges up, there's not as much current flowing through the circuit and the bulb slowly fades out. With the battery disconnected, it kind of does the exact same thing. Now the capacitor acts like a mini battery. It directs the current, but it doesn't have what batteries have. It doesn't have that chemical reaction going on to move the current through. So the current slowly fades out, and therefore the bulb also slowly fades out. So the time to charge a capacitor with a 10 ohm bulb is roughly about 15.4 seconds. The time to discharge the capacitor is about 20 seconds. And then when we double the resistance of the light bulb to 20 ohms, now the time to discharge that capacitor is 40 seconds. Since we are in an RC circuit, we now have to bring time into the equation, and now we get a time-dependent voltage. So from that, we can measure the voltage and the time, and then using an equation that we had and rearranging it, if we take the natural log of the change in potential over the initial voltage versus the time, we can get a slope which is equal to -1 over RC. From there, we can calculate the RC. From our graph here, the calculated RC is about 6.017 seconds. And then when we compare this to the value from the simulation, we get a very similar answer. So from the simulation, we multiply the resistance times the capacitance. So 30 ohms times 0.2 farads equals 6 seconds. So our two RC values are very close to each other. To wrap things up here, we have a few what-if questions. So what's different about a real ammeter compared to the simulation? So in real life, everything has some amount of resistance, whether that's very small, very minuscule, almost negligible, or something huge that can block most things. Also, ammeters are real objects, so they do have a limit to how much charge they can handle. With all those things being said, our simulation and real-life ammeters will differ slightly. How quickly would our ideal model predict the capacitor to charge, and would this prediction happen in real life? So our ideal model would predict the capacitor to charge instantly. This is because in the simulation, it counts the wires and everything else that doesn't have the resistance to have zero resistance. With that being said, since there's no resistance, the capacitor would charge instantly. However, in real life, this is not the case. Like I mentioned earlier, everything has resistance, if not just a little bit of resistance. The capacitor would still charge very quickly, but not instantaneously like in our simulation.